There's a lot of middle schoolers at the college right now, so hopefully my mic won't be picking up their noise, but if they do, then we'll have to deal with it. All right, so remember back in chapter 1, we talked about the criteria for life, and we used the acronym ROACHES, and the E stood for energy. And that is what we are going to be talking about in this chapter, over here in chapter 6. Okay. Well, actually, in this whole unit. So in chapter 6, we'll cover the basics of energy in living systems. We will have a little bit closer look at metabolism. We talked about metabolism really briefly back in chapter 3 when we were talking about monomers and polymers and our 4 different classes of biomolecules, but today we'll get into a little bit more detail of that. Okay, so here's our concept map for the chapter. Energy, we're going to define it as the ability to do work. We can put it into these 2 categories of kinetic energy or potential energy, and we'll talk about the first and second laws of thermodynamics. When we take that energy and we put it in the context of metabolism, this is where we're going to discuss enzymes in far more detail. We'll talk about how they speed up biological chemical reactions and how they are specific. Our enzyme proteins are going to be specific for the type of reaction that they do. We're going to categorize our chemical cell reactions into anabolic and catabolic. Anabolic, this is where we're going to build molecules from smaller things, and in catabolic reactions, we're going to break the. We're going to start big and break them down to small. In anabolic, we're going to start small and build them up to large or big. Let's talk about the flow of energy in living things. We'll talk about kinetic and potential energy. We'll talk about where does the energy for the biosphere actually come from. And then we'll talk about redox reactions. These are a little bit confusing to students, so we'll spend some time discussing those in detail. All right, so thermodynamics, if we look at this word, thermo means heat, dynamic means changes, so these are changes in heat. Okay, so this is the study of how energy transforms. Heat is a really easy and convenient way to measure energy, so we'll use that. And it's very important that, again, biology is interdependent with chemistry and physics, so all of the biological systems that we're going to talk about in this course and in your future are all going to be subjected to the laws of thermodynamics. Okay, so again, we've already defined energy as the capacity to do work. And we are going to have 2 major categories of energy. This is kinetic energy, the energy of motion, like we see in the waterfall. So the water is moving. So kinetic, this is the energy of movement. The water is moving down these steps of the waterfall and releasing that energy in the form of movement. Okay. And potential energy, this is stored energy. So this is not what Lake Powell looks like today. All this stored energy of this water behind Glen Canyon Dam. If Glen Canyon Dam had a catastrophic failure, right, then all this water that's stored behind it would then transfer from potential energy into kinetic energy, and we would have a release of a lot of energy all at once. Other forms of potential energy can be as chemical energy. The bonds in the glucose and lactose molecules of our ice cream cone, we can break those bonds to release the stored energy from those chemicals. Energy is going to be able to take on many forms. We can have mechanical energy, heat energy, sound, electric, light energy. So we're going to talk about light energy. We're going to talk about chemical energy. We'll talk about kinetic energy in this course. Okay. Again, like we said before, heat is a convenient way to measure energy, and we measure that in the form of calories. A calorie is defined as the amount of heat required to raise 1 gram of water 1 degree Celsius. And what's really important for us as biologists is that cells are really bad at using heat as an energy source. So when we talk about when chemical energy gets transformed to kinetic energy, some of that energy is going to get lost as heat because the cells can't use it. Okay, so heat is not a useful form of energy for cells. So energy from the biological world is driven by the sun. So we know, because we've lived on this planet for our whole lives, that the solar energy is going to power photosynthesis, which we'll talk more about later in this unit. That's going to provide energy for things that have to eat. So these are, so our organisms that can do photosynthesis, we're going to call those autotrophs, because auto, self, troph, to eat, they can feed themselves. Everything else in the ecosystem are heterotrophs, because they have to have other eating, so they have to eat other organisms for their energy. Okay, but let's kind of think about what's going on at the cellular level. If we have an event where we lose the sun, we have 8 minutes before all of the energy input into the ecosystem goes away, and our planet would die immediately, because energy is going to travel through the ecosystem. And so if our source gets cut off, then we have a limited time to use that. Okay. So in our autotrophs, our photosynthetic organisms, they're going to capture that light energy, and they're going to store energy in chemical bonds in the form of glucose primarily. Okay, so our redox reactions are actually short for reduction oxidation reactions. Okay, so it's just like an abbreviation. So when we have a reduction oxidation reaction, these are always paired, always, 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 always. Okay, so we have a particle A, we have our particle B. In this case, one of the electrons from particle A is going to be transferred. Okay, so here we are. We're going to take this electron from particle A, and we're going to shove it onto particle B. Okay, this means that now particle A has a positive charge because there's more protons than electrons. Okay, but our particle B is going to have a negative charge because there's more electrons than protons. Okay, so what we're going to say then is that because particle A donated or lost the electron, we say that particle A is oxidated. Okay, so this is the loss of an electron. The particle that is reduced is the particle that gains the electron. Okay, hold on, Julia. Wait. You just told me that we're gaining a thing to become reduced. That's backwards. Our particle B became more negative. And so as you become more negative, you get a lower charge. You become reduced. We'll talk about some examples of this in our next chapter, about how these particles that become oxidized and reduced, and why that's important for how we actually process that glucose when we need to create our high energy ATP molecules.